Our next topic is iterative compression. Let's say that we want to find a small feedback vertex set of a graph. So the problem that we want to solve has as input a graph G and an integer k, and the output is a feedback vertex set of G of size at most k. Of course, the graph might not have a feedback vertex set of size at most k, so we say it outputs one of those if one exists. And if no feedback vertex set of size at most k exists, then the algorithm will just say, I couldn't find one. Okay, and suppose somebody wants us to solve this problem, and they're giving us an algorithm. They're giving us an algorithm that has running time O star of 1.6 to the power n for a variant of this problem. And the variant is the compression version of the problem. So it's a compression version. Well, it's the same thing, except that we have an additional input S. And this additional input, what is it? Well, it's a feedback vertex set of G of size k plus 1. So there is already a feedback vertex set of size k plus 1 in the input, and the question is whether we can find one of size at most k. Then somebody gives us an algorithm for this compression version of the problem. And they ask us, well, can you now solve the feedback vertex set problem? Can you now find an algorithm that finds the smallest feedback vertex set, or feedback vertex set of size at most k, for any k? And of course we can do this because, well, now that we have access to this algorithm, what we can do is, well, we initially set S to be the whole vertex set. And of course that's a feedback vertex set. And we ask, well, now, is there a feedback vertex set of size n minus 1? N is our number of vertices. And if so, then the algorithm returns this feedback vertex set, and we can feed it into a new execution of this algorithm where, well, we give it this feedback vertex set of size n minus 1, and now the question becomes, is there a feedback vertex set of size n minus 2, etc. And we could keep doing this until the algorithm cannot find a feedback vertex set anymore. And then, of course, we have found a feedback vertex set of the smallest size. And so what's the running time of this algorithm? Well, it's O star of 1.6 to the power n times, how many times can we execute this algorithm? Well, at most n times. So indeed, we get an algorithm for the feedback vertex set problem. So the black subset here of the problem, where we don't have this additional input S, in time O star of 1.6 to the power n. Okay, so that's very nice. So from this red running time here, we get this black running time. Okay. But now let's assume that, well, somebody gives us, instead of a 1.6 to the power n time algorithm, they give us an algorithm with running time 1.6 to the power k for the compression version. Can we do the same thing? And let's say that they are interested in a parameterized algorithm that is exponential only in the size of the smallest feedback vertex set. So if there's a very small feedback vertex set, they don't want us to use a running time that's exponential in the number of vertices. So now, of course, we cannot do this because, well, once we start with the whole vertex set as our feedback vertex set, and we ask for a feedback vertex set of size 1 smaller. So n minus 1, which then becomes our k if we want to run this subroutine. Then we can't do it because, well, we already exceed the running time that we are allowed to use. So at the moment it's still unclear whether this leads to something. And in iterative compression, we will be able to exploit such running times even in the parameterized setting. And we will start with looking at algorithms for feedback vertex set and for minimum R hitting set. But we'll start with vertex cover as an example. So this works for any minimization problem. So there's a compression step which says that, well, given a solution of size k plus 1, can you compress it to a solution of size k? Or if not, then guarantee that there's no solution of size at most k. And then there's an iteration step, which now, well, we saw that, well, we cannot start from the whole graph and with a simple solution on this whole graph, because then we already have a running time that exceeds what we are allowed to use. So that's where the iteration step comes in. We start building the graph from small components. And this doesn't only work for graph problems. You could solve other kinds of problems where we build our instance incrementally and we keep a tally of small solutions for these instances so that in the end we get a small solution for the whole instance. So we incrementally build a solution to the given instance by deriving solutions starting from very small instances, solutions to larger and larger sub-instances. Let us first illustrate the technique using vertex cover as an example problem. So a vertex cover of a graph is of course a subset of vertices such that every edge of the graph has at least one endpoint in this subset. So, and we'll design a slow iterative compression algorithm for vertex cover just to illustrate the technique. So this will not be a competitive algorithm. So what's the compression version of the vertex cover problem? Well, the input is a graph G and an integer k, and a vertex cover of size k plus 1 of the graph. And the output is a vertex cover C star of size at most k if one exists. So how do we exploit the existence of this vertex cover of size k plus 1? So C star will contain some subset of vertices of C. This subset might be empty. And what we are going to do is we are going to guess the intersection between C and C star. By guessing, we mean that we go through all possibilities of how this intersection could look like. So what vertices are contained in the intersection of C and C star. And so C prime will be those vertices that are in this intersection. So we're going to go through all partitions of C into C prime and C prime bar. And C prime are those vertices that will be in our new vertex cover C star. And C prime bar will be those vertices that will not be in our vertex cover C star. And once we go over all partitions of C, then we have covered all possibilities. Okay, so we decided that we take all the vertices in C prime into our vertex cover, so we cover already some edges. And so we are not going to choose any vertex from C prime. Okay, but C prime, so the vertices of C prime, they covered some edges. So, but we know that, okay, so if this vertex V here covered some edges, we know that, well, if we're not adding V into the vertex cover, then these edges must be covered by, well, V's neighbors. It's the only vertices that can do the job. If V was actually adjacent to another vertex in C prime bar, then we would say, no, this partition doesn't work for us. Because, well, we know that at least one of those two vertices must be in the vertex cover. Okay. Okay, so this covers now also all the edges. So if we take the neighborhood of C prime bar into the vertex cover, this covers all the edges that are incident to C prime bar. Which other edges do we need to cover? We have to look at the edges in V minus C, but actually they don't exist. Because C was a vertex cover, so all of the edges had at least one endpoint in C. So this doesn't exist because V minus C is an independent set. Okay, so for this partition, our new vertex cover is now C prime union the neighborhood of C prime bar. If this new set covers all the edges, in other words, if C prime bar is an independent set, and, well, the size of the set, so the size of the set C star is at most k, then we return C star. And if not, we go to the next partition and try the next one, until we have tried all of them. If for none of them there was a solution, then we know that, well, the vertex cover that we get as part of our input, so this vertex cover C here, is the smallest vertex cover. Now, how do we solve the vertex cover problem? Well, we want to use this algorithm for the compression version to solve vertex cover. And we will start with, well, first of all, we order all the vertices of the graph, and we define G sub I as the graph induced on the first I vertices of this ordering. And so in our first step, we will process the graph G0 that contains no vertices, and then G1 that contains only one vertex, and then G2 that contains the first two vertices, etc. So at step I, we process the graph on I vertices that has all the edges between those I vertices that were in the original graph. Okay, so, and of course, when we have no vertex in our graph, well, we don't need any vertex in our vertex cover, so our first vertex cover will just be the empty set. So now at step I, where I is between 1 and n, we will find a vertex cover of size at most k of Gi, if one exists, using the compression algorithm. And so we use the compression algorithm with input Gi and Ci minus 1 union Vi. So what is Ci minus 1? Well, so it's the vertex cover that was found in the previous step. Some vertex cover of size at most k of Gi minus 1. So the set of vertices covered all the edges of Gi minus 1. Now we have added the vertex Vi. So, and of course all the additional edges that got added to the graph by adding this vertex are covered if we add the vertex Vi to the vertex cover. So we get the vertex cover from the previous vertex cover by just adding the new vertex. Now, if Gi has no vertex cover of size at most k, then of course G has no vertex cover of size at most k. Because this vertex cover must cover all of the edges of Gi already. And any vertices that will be added in the future will not help to cover these edges that are in Gi. Okay, so we are starting from the empty graph and add the vertices one by one. each time we compute a vertex cover of size most k, if one exists, and then we obtain a new vertex cover for the next step by just adding the new vertex that gets added to the graph. And then each time we compress again. So our final running time is, well, this iterative, so the number of iterative steps is at most n. So the running time only depends on the running time of this compression algorithm here. And so what did it do? It took a set of size k plus 1 and went through all partitions, and the rest was polynomial. So the running time is 2 to the power k plus 1, or O star of 2 to the power k. And well, we always have the same value of k here, and we can of course have smaller vertex covers, but in any case they have size at most k. So the final running time will be O star of 2 to the power k. Let's try and do the same for feedback vertex set. So in feedback vertex set, we have a multigraph as our input and an integer k. And the question is whether G has a feedback vertex set of size at most k. In the compression version of feedback vertex set, we also have a feedback vertex set S of size k plus 1. And the output is a feedback vertex set S star of size at most k if one exists. Let's start with the easy part, namely the iteration steps. Because this works exactly the same as for vertex cover. We just order the vertices from 1 to n, and we define the graph induced on the first I vertices as gi. Now a graph with no vertices has an empty feedback vertex set. And now for I varying from 1 to n, we will find a feedback vertex set of size above k of gi, and we call this feedback vertex set Si. And we will find it using an algorithm for the compression version with input gi and the previous feedback vertex set plus the new vertex vi. So if gi has no feedback vertex set of size at most k, then g of course has no feedback vertex set of size at most k either. And so suppose we have an algorithm for the compression version with running time O star of c to the power k. Then using this iteration, we can solve the feedback vertex set problem in time O star of c to the power k as well. Because we just repeat the same thing n times, and so the running time will be O star of c to the power k times n. So this will be our final running time then. We still need to solve the compression version of the problem, and we use the same approach as for vertex cover. So to solve the compression version, we will go through all partitions of this feedback vertex set S that's given to us. And so we'll partition it into two sets, S prime. Those are the vertices that we want to keep in our vertex cover. And S prime bar, those are the vertices that we don't want to have in our new vertex cover. So we'll try and find a feedback vertex set S star of G that is smaller than S. It contains all the vertices of S prime and none of the vertices of S prime bar. Equivalently, well, since we know that once we put a vertex into our feedback vertex set, we can just delete it from the graph. This is equivalent to finding a feedback vertex set S double prime of the graph G minus S prime. So those are those that we decided have to be in our feedback vertex set. And so S double prime must be smaller than S prime bar. And it cannot contain any vertex from S prime bar. So this gives us the following problem. So it's called disjoint feedback vertex set. The input is a graph G and an integer k, and a feedback vertex set S of size k plus 1 of G, and the output is a feedback vertex set S star of G of size at most k, and it should be disjoint from S. So S star intersect S should be empty. And of course we want to find such a feedback vertex set if one exists. Okay, so we went through all the partitions of the set S, and then we said, okay, for those vertices that we decided must be in our new feedback vertex set, we just delete them from the graph. And well, we don't want to use any of the remaining vertices for our new feedback vertex set. So our new feedback vertex set should be smaller, and it must not contain any vertices from this set S point bar. So that's how we obtain this disjoint feedback vertex set problem. So now let's say that we have an algorithm for disjoint feedback vertex set with some running time. How fast can we now solve the compression variant of the feedback vertex set problem? Well, let's say that disjoint feedback vertex set can be solved in time O star of d to the power k time. Now, what does the compression algorithm do? Well, it goes through all partitions of S, and well, for each of these sets S point bar, it does something. So let's say that so in the summation here, I will stand for the size of S point bar. Now, its size can vary from 0 to k plus 1, and so there's k plus 1, which is the size of S, choose I, which is the size of S point bar, many choices for S point bar. And so for each choice of S point bar, we will run the DISJOINT-FVS problem. And so its running time is d to the power k, and k is, well, the size of S prime bar plus 1. The plus 1 doesn't really matter for us. That will just be a constant factor in the running time. So the overall running time will be the summation from 0 to k plus 1 of k plus 1 choose I times d to the power I. And now we use the binomial theorem, which says that x plus y to the power n is equal to the summation from k equal to 0 to n of n choose k times x to the power n minus k times y to the power k. So of course here we need that, so the summation is from k equal to 0 to n, and so n here stands for k plus 1 over here. K down here stands for I up here. Okay, so we have k plus 1 choose I. So in the binomial theorem we have an n choose k. And then we only have one multiplicative factor here, which is d to the power I. So it's basically whatever we have on the bottom of the binomial over here, so which is a k. So basically we wouldn't have this factor. So this factor would just be, so x would be 1. And so y is equal to d. So meaning that the running time that we get in the end is d plus 1 to the power k. So the final running time will be d plus 1 to the power k. Okay, so which is also the final running time for the feedback vertex set problem. So now we still need to solve this disjoint feedback vertex set problem, and there we will get our hands dirty. Okay, so the input is a graph G in integer k, a feedback vertex set of size k plus 1, and now we want to find a smaller feedback vertex set, so one of size at most k, that is disjoint from the one that's given to us. Okay, so this is the feedback vertex set that's given to us, and so this is, well, the graph. This is the set of vertices v minus s, and we know that, well, if S is a feedback vertex set, then this is a forest. By the way, we also know that if S doesn't induce a forest, so this is a forest. If, well, the graph induced on S is not acyclic, then, well, since we are not allowed to put any of those vertices into the feedback vertex set, so if there exists a cycle in S, we will never be able to get rid of it. So it just means that, well, such a feedback vertex set S star doesn't exist. So this is actually our first simplification rule. So if the graph induced on S is not acyclic, then we will just return no. So it's our first halting rule. And so our algorithm will build up this set S star by first executing some simplification rules, and then let's see what happens later. Okay, of course, if we have exceeded our budget, if we haven't found a feedback vertex set yet, and k drops to less than 0, then we return no. So our last halting rule is when we are finished, when actually we have found a feedback vertex set S star, then we return that feedback vertex set. Okay, now we have a few more simplification rules. So let's see. You could, for example, look at this vertex. So what we see is, well, we see that it creates a cycle with what is already in S. So we know that we are not going to put any vertex from S into our feedback vertex set. So the only way to break the cycle is by adding this vertex here to the feedback vertex set. So that's our first simplification rule. If there exists a vertex in A, such that this vertex induces a cycle together with the vertices in S, then we will add V to the set that we are constructing, S star, and remove it from the graph. Okay, so let's remove this vertex. It disappears from the graph. Okay, so what's next? If we have a vertex of degree 1 anywhere in the graph, then we know that, well, it will not contribute to any cycle. This is true for degree 0 vertices as well. So if we have a vertex with degree at most 1, then we can just remove it from the graph. Okay, so we'll remove this vertex. Next, let us look at degree 2 vertices. Namely, let's focus on this vertex here. Okay, so we know that, so we had a simplification rule for feedback vertex set for degree 2 vertices. So, and there we said that, well, if we have a degree 2 vertex, then every cycle that goes through this degree 2 vertex also goes through its neighbors. So instead of putting this degree 2 vertex into the feedback vertex set, we might as well add a neighbor instead. But now you have to be careful because, well, if we look at this degree 2 vertex, for example, well, both its neighbors are in S. So we can't really do this for this degree 2 vertex because, well, we know that the neighbors will not be added to our feedback vertex set. The only option is to add this vertex to the feedback vertex set. But if we have a vertex like this one, where one of the neighbors is in A, then we can use this argument. Then we can shortcut the cycle and remove this vertex and connect it to neighbors instead. So the degree 1 vertex disappeared. Now we are looking at this vertex. It has degree 2, and at least one of its neighbors is in A. What we are going to do is we add an edge between the neighbors of the vertex V, even if there was already an edge, and we remove V from the graph. Okay. So now I think we are done with our simplification rules. So now we're going to do some branching. We will select a vertex in A that has at least 2 neighbors in S. Why does such a vertex exist at all? So A is a forest. So it contains trees. An isolated vertex is also a tree. And we will look at isolated vertices as a special case. So, okay, let's say that we have an isolated vertex in A. Then, because of our simplification rules, well, it must have at least 2 neighbors. It cannot have degree 0, it cannot have degree 1 in the graph G. So its 2 neighbors must be in S. But it could, of course, be that A doesn't have any isolated vertices, in which case we will actually look at a leaf of some tree in the graph induced on A. And so we know that our graph cannot have any degree 1 vertices. So this leaf in A here must have other neighbors, and they must be in S. So it must have at least one other neighbor, because the degree at most 1 rule cannot be applied. Okay, and we also know that the degree at most 2 rule, or the degree 2 rule, cannot be applied because our instance is simplified. So it cannot be the case that, well, the degree of this vertex is 2 and one of its neighbors is in A. So that meaning that it must have another neighbor in S. So now we get at least one vertex that has at least 2 neighbors in S. So now we are going to branch. We select such a vertex and branch into 2 subproblems. So either V is in the feedback vertex set that we are constructing, in which case we remove it from the graph and decrease k by 1. So we do make some progress. Or V is not in the feedback vertex set. And if V is not in the feedback vertex set, well, we can encode this into our problem by adding it into S. So let's say this is our vertex V, and we decide to not add it to the feedback vertex set, we just move it into S. Okay, but okay, it might be the case that in this case we don't make any progress in terms of K. So how do we argue that this algorithm is fast? So here K decreases by 1, which is nice, but here, well, K doesn't decrease. But so we have to argue somehow that, well, we cannot keep doing this operation over and over again. Why not? Well, it's kind of because, well, we know that V, together with the vertices in S, doesn't create a cycle because of one of the simplification rules. So this means that, well, these 2 vertices here, they are not connected inside S. So if we look at the connected components in S, well, these 2 vertices belong to 2 different connected components. Now, once we add V into S, we see that the number of connected components of S decreases by 1. So, and actually, every time we do this, every time we move a vertex from A into S, the number of connected components of S will decrease by 1. So we could have started with k plus 1 connected components, but then we know that we can move at most k vertices from A into S. So once we have done this operation k times, we cannot do it anymore. Same as for this operation, once we decrease k times, we cannot do this operation anymore. So in both cases, something good happens in terms of k. Here k decreases, and here, well, the number of connected components, which is initially at most k plus 1, decreases, and it cannot go less than 1. Or it could go to 0 if the degree 1 rule eliminates everything in S. But it cannot go less than 0. Okay, and this is how you can then prove that the algorithm has running time O star of 4 to the power k. So you would need to define some measure that decreases in both branching steps, and you would then upper bound the measure by probably something like 2 times k. Okay, so the disjoint version can be solved in time 4 to the power k, meaning that, well, the compression version can be solved in time 5 to the power k, which also means that feedback vertex set can now be solved in time O star of 5 to the power k time. Next, we look at minimum R hitting set. So in the hitting set problem, we of course have a set system as our input, where we have elements and sets of elements. We have an integer k, which is our parameter, and the question is whether the set system has a hitting set of size at most k, so a set of elements that intersect all of the sets. And we speak of R hitting set if the maximum set size is at most R. So we have a rank R set system, and the rank of a set system is the maximum size of a set in the set system. So we know that in general, if we don't restrict the maximum set size, then hitting set is W2 hard. It's complete for W2. But if we restrict the maximum set size to some constant R, then actually there is an easy R to the power k branching algorithm. Because, well, we could look at some set of size R, or set of size at most R, and we know that, well, we have to hit this set. So there's only at most R many possibilities of choosing a vertex to hit this set. So we could branch into R subproblems where each time we add one of the elements of the set into our hitting set. But now we are going to try and do faster. And we are going to use iterative compression again. And so let's look at the compression variant of the problem. So we have a set system, an integer k, and also a hitting set of size k plus 1 of the set system. So x is our hitting set, and we want to compute a new hitting set x star of size at most k if one exists. Okay, so we know that, well, this is a hitting set. So we know that for every set in our set system, at least one of the elements is inside x. Okay, and now what we are going to do is we again go over all partitions of x into, well, those we want to keep in our hitting set and those we don't want to have in our hitting set. Okay. So for those vertices, or for those elements that we want to keep in our hitting set, well, we know that well, we have already hit all these sets, so we can just remove those sets. We can remove these elements because they have done their job. For those elements that are not going to be in our hitting set, well, we can just remove their elements because they are not going to help us hit any sets. But the set still remains. Okay. What we need to do is we need to reject a partition if there's some set that is completely contained in x prime bar, because we are never going to hit such a set. But for the remainder, we just remove those sets that we have already hit, and we remove all the elements of x prime from the instance, and we also remove all the elements of x prime bar from the instance. So what we need to compute now is a hitting set for the remaining instance. So what's the remaining instance? Well, it's v prime h prime, where, well, we have removed all of these elements that occurred in x, and we have removed all the sets that intersect at least one element from x prime. And so we need to find the hitting set of this instance of size at most k minus the size of x prime. How fast can we do this? Well, we now get a new instance of a hitting set problem, right? So now we have, well, these remaining sets that still need to be hit. And we can use at most k minus the size of x prime many elements to hit those. Okay, but one very important observation is that, well, this instance here, that's actually now an instance of not just minimum k hitting set, but, or minimum r hitting set, but minimum r minus 1 hitting set. Why is that? Well, we know that every one of these sets had at least one element inside of x. And we removed all of x from the instance, meaning that, well, for every set, we removed at least one element from the instance. So we have decreased the maximum set size by at least one. So of course, if we find a solution, then we return it. Okay, so that's the observation that all of these sub-instances have maximum set size at most r minus 1. So suppose that r minus 1 hitting set can be solved in time, well, some constant to the power k time. So, and we denote this constant by alpha sub r minus 1. Then, well, the compression version of r hitting set can be solved in time, well, the summation of s going from 0 to k of k choose 1, k plus 1 choose s. And then, so if s is the number of elements that we have added to our hitting set, then we need to choose k minus s more elements of our hitting set. So we have an alpha r minus 1 to the power k minus s. And here again we can use the binomial theorem and conclude that the running time is O star of alpha r minus 1 plus 1 to the power k. One observation is that 2 hitting set is equivalent to vertex cover. So in 2 hitting set, we can have sets of size 0, 1, and 2. If we have a set of size 0, then we know that we have no instance because there's no way of hitting this set. If we have a set of size 1, then there's only one way to hit the set, and so we have a simplification rule that adds this element that's contained in the size 1 set into the solution, meaning that we would remove it from the instance and also remove all the sets that contain this element from the instance, and we would decrease our budget by 1. So we are left with only sets of size 2, and if we only have sets of size 2 and we want to hit every set, this is equivalent to covering all the edges of a graph. So in 2 hitting set, we can just convert this to a graph and compute a smallest vertex cover in time 1.2738 to the power k, where k is the size of the vertex cover. For 3 hitting set, there also exists a fast algorithm. So an algorithm by Wallström solves it in time 2.0755 to the power k. Okay, so we now have a way to express the running time for the compression problem in terms of the running time of R-1 hitting set. Okay, now let's go to the iteration step. And here we have a choice. So let's order again our elements from V1 to Vn, and Vi is the first I elements of our set of all elements. But now Hi, so the sets, for instance number I, will only contain those sets where, well, their elements are completely contained in V1. So suppose, for example, that we have a set containing, I don't know, 4 elements. So our choice is that we are only going to consider the set once all 4 elements are in our set Vi. So this is important because, well, suppose, for example, that we have like one vertex that is contained in many sets. There could be arbitrarily many sets. So, and let's say we first consider this element, then this element, then this one, this one, this one, this one. So if we, by doing this, if we look at these smaller sets, then we would think that, well, we will need at least one element for each of these smaller sets. And then only in the end, when we consider vertex number 7, we discover that, oh, we could have basically hit all of these sets with just one vertex. So that's a situation that we don't want to occur, that, well, our solution size increases and then decreases. Because, well, in the end, we want a running time that is, well, efficient in terms of k. And, well, if in intermediate steps, well, this parameter can become very large before it becomes much smaller again, then potentially our algorithm will be exponential in the maximum of these fluctuations of the parameter. So we don't want this to happen. We want to make sure that we only add a set to our instance once we have basically discovered all its elements. And namely, then we can say that, so if we have a solution for instance number I-1, and now we add a new element, so the new sets that we consider all contain this element, and only previously known elements. So then, again, we have this property that, well, the best solution that we can find for instance number I has its size sandwiched between the size of the best solution for instance I-1 and, well, the same size plus 1. So if we find the smallest hitting set of instance number I, then we know that, well, the size of the solution for instance number I is either the same or one more. And we also know that, well, in the end, the solution that we get in the end will not be smaller than, well, this solution, the best solution for instance number I. Okay, so if we keep doing this, so we can start now from r equals to 3. So, and there we had a running time using Wallström's algorithm of, it was 2.0755 to the power k. Now, so that was for 3 hitting set. So now if we want to solve 4 hitting set, what do we get? So for 4 hitting set, let's go back. So the iteration here, again, will not incur any exponential factor into our running time. So that's just a polynomial factor. So here we saw that, well, if we can solve r minus 1 hitting set in time alpha r minus 1 to the power k, then, well, this compression problem and also r hitting set can be solved in time, well, at the same time, but we add one more to the base of this running time. So an algorithm for 3 hitting set in time 2.0755 to the power k leads to an algorithm for 4 hitting set of 3.0755 to the power k. And for 5 hitting set, we get a running time of 4.0755 to the power k, and so on. So we can summarize this by theorem 2, where we basically take, well, this number here and subtract 0.9245. Okay, so we get a parameterized algorithm like this, and now we know that by monotone local search, since this is a subset problem, we can now use monotone local search to derive also a running time in terms of n. So and what we get here is 2 minus 1 divided by, well, this base of this running time. So 2 minus 1 divided by r minus 0.9245, and all of it to the power n. So whenever r is a fixed constant, this will give us something faster than 2 to the power n. But of course, if r becomes large, then this method doesn't work anymore. Okay, so you can read much more about iterative compression in these book chapters. And these are the references.